So let's now take a look at example sheet 5. So if we look at question 1, then basically the question is saying that two identical waves are emitted from the same source in phase. So if the amplitude, frequency and wavelength of both waves are 0.1 meters, 6 hertz and 5 meters respectively, calculate the combined displacement resulting from the interference of the waves at 0.2 meters from the source and 6 seconds from the start of the wave generation. Okay, so if we look at what this means, then basically we've got two waves that look exactly the same. So basically the two waves look exactly the same, and they have exactly the same properties. So if they are emitted from the same source in phase, then basically they will they're going to constructively interfere. So what that means is we're going to get a resulting waveform that actually has double the amplitude of each of these individual waveforms. And the reason for this is that basically if we look for the resultant of two waves at any point in space, then basically the way to look at the resultant is to just add the displacements of those two waves at that given point in time. And so here, if we're adding the displacements together, we're going to end up with 2 times the displacement. And that comes from the fact that we can just add, if we have one wave, so wave 1 is given by A1 sine of, I'll call it phi, just a phase relationship where phi is equal to omega t minus kx. Then if that is the resultant of two waves added together, then that will be A2 sine phi, and say we're adding A3 sine phi, so another wave there. Then basically we just add these two together and that gives us a resultant waveform. So in this case these two waves are exactly the same. So if this wave is the same as this and we add it to itself, then that's just going to be equal to 2 times by A sine phi, which of course is omega t minus kx. Okay, so this is where this relationship comes from. If we have two waves that are identical and we add them together, then the resultant is going to be 2 times by the original wave equation in this case. So here we're asked to calculate the combined displacement resulting from the interference of the waves at a point 2 meters from the source and 6 seconds from the start. So x is going to be equal to 2 meters because x is the distance from the source, and our time t is going to be equal to 6 seconds. Okay, so all we need to do is put these values into this equation here, and that will give us the value of the displacement of the wave at that point, basically. So basically let's do that. So for this question we've got y is equal to 2 times by the amplitude, which is 0.1 sine omega, which was given as, we don't know that yet, t minus kx. What we need to do in this case is we need to convert the frequency and the wavelength into our omega and our k values. Okay, so to do that we know that this k value here, k is actually equal to 2 pi divided by lambda. So in this case our wavelength was given as 5 meters, so that's 2 over 5 times by pi, and then our omega value is equal to 2 pi times by the frequency. So remember, omega is the angular frequency, so it's basically doing 2 pi radians. The number of times it covers this 2 pi radians of rotation in a second is the angular frequency. So to calculate omega, we multiply the actual frequency by 2 pi to give us the right answer there. So in this case our frequency was 6 hertz, so that's actually going to be equal to 12 times by pi. So we can put that into our equation. So now y is equal to 2 times by 0.1 sine of omega, which is 12 pi times by t, which is 6, minus k, which is 0.5 pi times by x, which was 2. Okay, 0.2 meters from the source. Yeah, it's 2. Okay. So if you calculate that, if you just put the values into the equation, then you'll get an answer of minus 0.118 meters. Okay. So the key things here are basically you're adding these two waves together, but because they're exactly the same, then the resultant is just double the amplitude of that waveform. So basically our equation is displacement is equal to 2a sine omega t minus kx. Put those values into the equation, having calculated what the wave number and omega are from the frequency and the wavelength, and that allows us to calculate the results of the equation. Okay, so question 2. This is a question about noise cancelling headphones. So it's saying that a pair of noise cancelling headphones are subjected to an external sound with a constant frequency of 200 Hz. Now, just as a reminder of how noise cancelling headphones work, if we look back at our lecture notes, you can see that noise cancelling headphones work by having an external microphone. So I have a microphone mounted on the outside of the headphones that records the kind of ambient sound around the listener to the music. So inside the headphones there are some special electronics that capture that ambient sound, and they invert it and then subtract that signal from the actual music signal. So what this has the effect of is basically it kind of subtracts the background noise from the headphones, which means that you just leave the music signal, so you can hear the music really clearly even if you're in quite a loud place like on a bus or on an aeroplane. So the first part of this question is asking us to draw a displacement time curve of the external waveform showing 2 full cycles of the oscillation, and that assumes that the maximum displacement has a value of a. So here I'm going to draw my displacement time curve. So my displacement time, I'll just have a value of y on here, and my time here t. Now I know my unit of t here is in seconds. I'm not given the actual unit for displacement here. It would actually normally for sound beam be like kind of intensity, but it could be a voltage if we're measuring it on a voltmeter or something. So we don't necessarily have to put a unit here yet. But basically we do have to mark on here that we have a maximum value a, which is equal to the displacement of our wave. So we have to draw 2 full cycles of the oscillation. So basically I'm going to start somewhere. I'm going to start at the origin for my waveform here. I'm going to go 1 full cycle, 2 full cycle, something like that. Okay. Now because I know that this the frequency for this waveform is 200 Hz, that means it's happening sort of 200 times per second, basically, if you've got something with 200 Hz. So if you divide 1 second by 200, that's going to give you the time taken for one complete oscillation of the cycle. So in that case, that's 0.005 seconds or 5 milliseconds. So I can mark a unit on my scale here of 5 milliseconds, and 2 will be 10 milliseconds. So I can put that on my graph there as well. And that's basically it, because I've summarised all the information that's been provided in the question. So it's 2 full cycles, I've got some units on the x-axis, I've got a unit on the y-axis that describes my waveform. So then I've got to draw the corresponding waveform that headphones will generate to cancel out this external noise. Well, what we're doing here is we're using the principle of superposition of waves, but to generate a completely destructive interference. So the waveform I generate to actually cause that to happen is completely out of phase with the first waveform. So my waveform will be the complete opposite, so it will look something like this. Okay, so you can see at any point on this waveform, if I add the 2 values together, I get a value of 0. So here this peak and this peak are the same distance from the x-axis, so if I add that value together with that one, I get 0, so it cancels. So these points here are 0. Anywhere along this waveform, if I add these 2 displacements together, they cancel to leave me a value of 0, which is how the noise cancelling headphones work. Okay, so for question 3, we've got 2-point source of coherent waves are separated by 50 millimeters. And we're going to calculate the wavelength of the waves as a separation between 2 successive interference maxima observed at a difference of 1.5 meters from the source is 30 millimeters. So this is our classic kind of Young's double slit arrangement, where we have 2 point sources of light in the Young's double slit experiment, but it actually works with any kind of wave. It could work with sound or even water waves. And these are separated by 50 millimeters. So let's draw out what the question looks like, so we can start to be able to solve it. If we draw a line going from these two sources to a screen here, then what we're saying is that we have a number of interference maxima along here, and the separation between each one of these is 30 millimeters. And the distance from the sources to the screen, I'll mark on here, is 1.5 meters. Okay, so what we need to do is actually calculate the wavelength of the illumination to provide this kind of interference pattern. So this is basically a double slit experiment. So the equation we use for this is x to the n is equal to n lambda d over small d. Okay, so this x to the n is the distance from the central fringe here to the next fringe, or the nth order fringe, basically. So what I can do is it will tell me the distance between this fringe and this fringe if I change this value of here from 1 to 2. So basically, each of these distances is always the same. By summing these together, we change this value of n, which is how the equation works. Okay, but let's keep it simple. We're just measuring from the 0 fringe to the 1 fringe here, which means n is equal to 1. So basically, this value here disappears because it's just 1 times the rest of the equation, and we'll do x to the 1. So basically, x to the 1 is equal to lambda d over d. So the big D here is the distance from the sources to the screen, and the small d is the distance between the two sources here. And lambda is what we're going to calculate because that's the wavelength of the light, or the wave in this case. So we need to rearrange this equation in terms of lambda. So if we rearrange this, then lambda is equal to small d times by x, and x1 is this distance here, divided by large D. Okay, so I can actually put values into that equation. So the small d here is 50, I'm going to convert that to meters, so it's 0.05 meters, times by this distance here, x1, which is 30 millimeters, so times by 0.03 meters, divided by this distance here, d, which is the distance from the sources to the screen, so it's 1.5 meters. Okay, so if I calculate that, then that gives me a result of 0.001 meters, which of course is equal to 1 millimeter. Okay, that's the answer to question 3. So let's now look at question 4, which is basically asking us what the angular width of a diffracted beam when plane waves are passed through a slit of width 0.1 millimeters. Okay, so this is our single slit diffraction work that we did in the lectures in class. So here we can see that a single slit normally produces a wide central fringe, which has 2 minima located either side of that. So we can actually calculate what the angle is of that large central diffraction pattern from the single slit. So we call this basically the angular width. So if I have my slit here, I have some kind of illumination source like a bulb on the other side of that, then if I look at a screen, I can determine this kind of angular width of this. If you imagine this is a bright light on the screen, I can determine what this angular width is of the slit. So and that's given by the equation that sine of theta is going to be equal to lambda divided by a, where a is the slit width. So if we look at the first part of the question, basically is asking us what that angle would be if the waves had a wavelength of 600 nanometers. So part A is if lambda equals 600 times by 10 to the minus 9 meters. Okay, so in that case, theta is just going to equal to for lambda over a, which is going to be 600 times by 10 to the minus 9, or 6 times 10 to the minus 7, divided by the slit width, which is 0.1 millimeters, which is 0.0001 meters. Okay, so I can calculate that, and that's going to give me a value of 0.69 degrees. Okay. If I do the same for part B, so now it's if lambda is equal to 6 microns. This is a much bigger, also longer wavelength. Then I just do the same thing again. So theta is equal to sine to minus 1 of lambda over a, which in this case is 6 times by 10 to the minus 6. Remember, micro is times 10 to the minus 6. Divided by the slit width, which is unchanged, which is 0.001 meters. And so that's going to give me a value, if I calculate that, of 6.9 degrees. Okay, and that's it. So finally we come to question 5, which is a diffraction grating. So this diffraction grating has 300 lines per millimeter, and it's used to generate a diffraction pattern using a laser pointer. So this is just like the example we did in the lecture. So it's telling us that the first order maxima is 24 centimeters from the central fringe. So if we draw this, we have our grating here, our laser beam comes here. If we have a straight through point to our central fringe, then we have this diffracted fringe at a point somewhere here, which is 24 centimeters apart. And the distance from the grating to the screen here is 1.2 meters. And it's asking us to calculate what is the wavelength of the laser light. Okay, so what we're going to use here is a diffraction grating, we need the diffraction grating equation. So here d sine theta is equal to n lambda. So the theta in this equation is this distance here, okay? So this is the angle at which it's being diffracted. D is the distance between slits in the diffraction grating, which is normally a really, really small number. N is, once again, the number of the order of diffraction here. We're looking at n equals 1, so that's just going to equal 1 in our equation here. And lambda is the wavelength of the laser light, which we're being asked to calculate here. So basically, if I just rearrange this equation very simply, if that becomes 1, then lambda is just equal to d sine theta. Okay, but the challenge is we don't currently know theta. We don't know what this angle is. What we do know is this length and this length of this effectively this right angle triangle that's formed here. So in order to calculate theta, if our angle is here, we know the opposite side and we know the adjacent side, but we don't know the length of the hypotenuse. So we can state that tan theta is equal to the opposite side divided by the adjacent side, which is equal to 0.24 meters divided by 1.2 meters. Which is equal to 0.2. So then theta is going to be equal to tan times 1 of 0.2, which is equal to about 12.6 degrees. Okay, so then if we put that back into our equation here, then lambda is equal to d, which we have to calculate again. So basically, lambda is equal to d sine of 12.6 degrees, but d we have to calculate because we know that the grating, the number of lines in the grating, is 300 lines per millimeter. So basically, 300 lines per millimeter is equal to 300,000 lines per meter. Okay, so to work out what the average spacing is, we divide 1 metre by 300,000, which gives a value of 3.33 times by 10 to the minus 6 metres. Okay, so finally lambda is equal to 3.33 times by 10 to the minus 6 times by sine 12.6, and that's going to give us an answer of 6.54 times by 10 to the minus 7 metres, which is 654 nanometers. Okay, so that's the end of example sheet 5. As ever, if you have any questions about the solutions, then contact me by email. Okay, thank you.